learning outcomes. After studying this module, you shall be able to number 1, know the concept of hypothesis and type of errors. Number 2, know about chi-square test. Number 3, know about t-test. 4, know about f-test. And 5, application of test of significance in forensic science.
Null and alternative hypothesis. Let theta denote the parameter of interest. This may be the average monthly sales or average productivity or average wages or even difference of wages in organized and unorganized sectors or proportion of visitors to a shopping center who actually make a purchase, etc. Let theta naught denote the value of the parameter as the initial claim under the null hypothesis. This is also known as the null value. The null hypothesis is then stated as h naught equals to theta is equal to theta naught. It is the hypothesis of status quo. The possible alternative hypotheses are number 1, h1 is equal to theta greater than theta naught, or number 2, h1 equals to theta less than theta naught, or number 3, h1 is equal to theta equals to theta naught. That is, either theta is less than theta naught or theta is greater than theta naught. These are known as the upper tailed, the lower tailed, and the two-tailed test respectively. The alternative hypothesis has implications for the null hypothesis. Thus, h1 is theta greater than theta naught, that is, h naught is equal to theta less than equal to theta naught. Upper tailed or right tailed test. h1 is theta less than theta naught, h naught theta greater than equal to theta naught. Lower tailed or left tailed test, and h1 is theta not equal to theta naught, h naught theta equals to theta naught. Two-tailed test. To test the null hypothesis, we need to first draw a random sample from the population and then apply a decision rule that uses the sample observations. It is important to set up the hypothesis correctly in the light of the problem situation. The alternative hypothesis is determined before any data are collected. It is based on the belief about the possible range of values of the parameter in the event the null hypothesis is not supported by the sample data. For the one-sided test, we would consider the alternative hypothesis to be plausible if sample data suggests the true value of the parameter is much higher than the null value, upper tail test, or much less than the null value, lower tail test. Similarly, in the two-tailed test, the alternative hypothesis is considered true if the sample data suggests the true value of the parameter is much higher or much lower than the null value. That is, the true value is significantly different from the null value.
Let us now understand what a test procedure is. Test procedure is a rule for deciding whether to reject or not to reject the null hypothesis based on sample information. The test procedure has two components. First is a test statistic derived from appropriate sample statistic, which is a function of sample observations. Second is the rejection region, which consists of those values of the test statistic for which the null hypothesis is rejected in favor of the alternative hypothesis. The decision rule for deciding whether to reject or not to reject the null hypothesis depends on the specified rejection region. Steps in the test of hypothesis. First, identify the parameter phi, for example, population mean mu, proportion p, variance sigma square, etc. Second, determine the null value phi naught from the given problem. Third, state the null hypothesis h naught equals to phi naught and the appropriate alternative hypothesis as required by the given problem, which can be h1 can be phi being greater than phi naught or phi being less than phi naught or phi being not equal to phi naught. Fourth, give the formula for the test statistic. These can be z-test, t-test, chi-square test, f-test. Fifth, calculate the applicable sample statistic phi hat from sample observations. For example, x bar, x by n, s square, etc. Sixth, calculate the value of the test statistic z, t, chi-square f using calculated value of the sample statistic. 7. State the rejection region using desired critical values of the test statistic. The critical values of the test statistic and the rejection region will both depend on how the alternative hypothesis is defined. 8. Apply the decision rule to reject the null hypothesis if the calculated value of the test statistic falls in the rejection region, and do not reject otherwise at the alpha level of significance. 9th, state the conclusion in terms of the problem posed. Now we are going to discuss type 1 and type 2 errors. Even in the best research projects, there is always a possibility that the researcher will make a mistake regarding the relationship between two variables. There are two possible mistakes or errors. The first one is called the type 1 error. This occurs when the researcher assumes that a relationship exists when in fact the evidence is that it does not. In type 1 error, the researcher should accept the null hypothesis and reject the research hypothesis, but the opposite occurs. The probability of committing a type 1 error is called alpha. The second type of mistake is called the type 2 error. This occurs when the researcher assumes that a relationship does not exist when in fact it does exist. In type 2 error, the researcher should reject the null hypothesis and accept the research hypothesis, but the opposite occurs, and the probability of committing a type 2 error is called beta. Now we are going to discuss chi-square test, student's t-test and f-test, which are commonly used for hypothesis testing. Chi-square test. For nominal and ordinal data, chi-square is used as a test for statistical significance. For example, we hypothesize that there is a relationship between the type of treatment program attended and the improvement in the mental condition of the patient. We gather the following data. Type of treatment can be A and B, and improvement in mental conditions is 200 and 250 respectively, and the total is 450. The patients healed are 300 and not healed are 150, that is a total of 450. Now to compute chi-square, a table showing the joint distribution of the two variables is needed. We have the table of patients healed by the type of treatment attended. These are the observed frequencies. Chi-square is computed by looking at the different parts of the table. The cells of the table are the squares in the middle of the table containing numbers that are completely enclosed. The cells contain the frequencies that occur in the joint distribution of the two variables. The frequencies that we actually find in the data are called the observed frequencies. In this table, the cells contain the frequencies for patient who underwent treatment A and got healed, that is n equals to 175, and who didn't get healed is n equals to 25. And the frequencies for patients who underwent treatment B and got healed is n 125, and those who did not get healed are 125. The total columns and rows of the table show marginal frequencies. The marginal frequencies are the frequencies that we would find if we looked at each variable separately by itself. For example, we can see in the total column that there were 300 patients who got healed and 150 patients who didn't. We can say that in total there were 200 patients who underwent treatment A and 250 patients who underwent treatment B. Finally, there is the total number of observations in the whole table called n. In this table, n is 450. Calculation of chi-square test. First, display observed frequencies for each cell. Second, calculate expected frequencies for each cell. Third, calculate for each cell the expected minus observed frequency squared divided by the expected frequency. And fourth, add up the results for all the cells. To find the value of chi-square, we first assume that there is no relationship between the treatment attended and whether the patient is healed. If we look at column total, we can see that 350 out of 450 patients got healed, or 66.7% of the patients under the treatment got healed. We can also see that 150 of 450 patients did not get healed, or 33.3% of the total patients under treatment did not get healed. If there was a relationship between the type of treatment attended and the success in healing the patient, then we would expect 66.7% of patients of both types of treatments to get healed and 33.3% of patients of both types of treatment to not get healed. The first thing that chi-square does is to calculate expected frequencies for each. The expected frequency is the frequency that we would have expected to appear in each cell if there was no relationship between type of treatment and patients healed. The way to calculate the expected frequency is to multiply the column total for that cell by the row total for that cell and divide by the total number of observations for whole table. For the upper left hand corner cell, multiply 200 by 300 and divided by 450. We get 133.3. For lower left hand corner cell, multiply 200 by 150 and divided by 450. We have 66.7. For upper right hand corner cell, multiply 250 by 300 and divided by 450. We get 166.7. And for the lower right hand corner cell, multiply 250 by 150 and divided by 450, we get 83.3. This table shows the distribution of the expected frequencies, that is, the cell frequencies we would expect to find if there was no relationship between the type of treatment and patients healed. Note that chi-square is not reliable if any cell in the contingency table has an expected frequency of less than 5. To calculate chi-square, we need to compare the original observed frequencies with the new expected frequencies. For each cell, we perform the following calculation. First, subtract the value of the observed frequency from the value of the expected frequency. Second, square the results. And third, divide the result by the value of expected frequency. For each cell above, we have the following table. To calculate the value of chi-square, add up the result for each cell. The total comes out to be 70.42. Degrees of freedom. We cannot interpret the value of chi-square statistics by itself. Instead, we must put it into context. If the value we obtain for chi-square is large enough, then we can say that it indicates the level of statistical significance at which the relationship between the two variables can be presumed to exist. However, whether the value is large enough depends on two things. First, the size of the contingency table from which the chi-square statistic has been computed, and second, the level of alpha that we have selected. The larger the size of the contingency table, the larger the value of the chi-square will need to be in order to reach statistical significance if other things are equal. Similarly, the more stringent the level of alpha, the larger the value of chi-square will need to be in order to reach the statistical significance if other things are equal. The term degrees of freedom is used to refer the size of the contingency table on which the value of chi-square statistic has been computed. The degrees of freedom is calculated as the product of the number of rows in the table minus 1 times the number of columns in the table minus 1. For the table with 2 rows of cell and 2 columns of cells, the formula is degrees of freedom equals to 2 minus 1 multiplied by 2 minus 1. That is 1 into 1, which is equals to 1. For a table with 2 rows of cell and 3 columns of cells, the formula is degrees of freedom equals to 3 minus 1 multiplied by 2 minus 1, which is 2 into 1, that is 2. For a table with 3 rows of cells and 3 columns of cells, the formula is degrees of freedom equals to 3 minus 1 multiplied by 3 minus 1, which is 2 into 2, that is 4. The level of alpha can vary, but the smaller the value, the more stringent the requirement for reaching statistical significance becomes. Alpha levels are often written as p-value or p equals to 0.05. Usual levels are p equals to 0.05 or the chance of 1 in 20 of making an error, or p equals to 0.01 or the chance of 1 in 100 of making an error, or p equals to 0.001 or the chance of 1 in 1000 of making an error. Interpretation of the results. If the computed value of chi-square equals or exceeds the value indicated in the table for the given level of alpha and degrees of freedom, then the researcher can assume that the observed relationship between two variables exists and rejects the null hypothesis. This gives support to the research hypothesis. Next, we move on to discussing t-test. T-tests are the tests for statistical significance that are used with interval and ratio level data. T-tests can be used in several different types of statistical tests. First, to test whether there are differences between two groups on the same variable based on the mean value of that variable for each group. For example, do students at private schools score higher on the SAT test than students at public schools? Second, to test whether a group's mean value is greater or less than some standard. For example, is the average speed of cars on freeways in California higher than 65 miles per hour? Third, to test whether the same group has different mean scores on different variables. For example, are the same clerks more productive on IBM or Macintosh computers? Calculating a value of t. First, state the research hypothesis, that is, the average salary of male graduate assistants is higher than the average salary of female graduate assistants at CSULB. Second, state the null hypothesis. There is no difference in the average salary of male and female graduate assistants at CSULB. Third, state the level of alpha. Select the level of alpha such as p equals to 0.5, p equals to 0.1 or p equals to 0.001. Fifth, stipulate whether the t-test will be one-tailed or two-tailed test for significance. And sixth, calculate t. Like other statistics, the t-test has distribution that approaches the normal distribution, especially if the sample size is greater than 30. Since we know the properties of the normal curve, we can use it to tell us how far away from the mean of the distribution our calculated t-score is. The normal curve is distributed about a mean of 0 with a standard deviation of 1. A t-score can fall along a normal curve either above or below the mean, that is either plus or minus some standard deviation units from the mean. A t-score must fall far from the mean in order to achieve statistical significance. That is, it must be quite different from the value of the mean of the distribution, something that has only a low probability of occurring by chance if there is no relationship between the two variables. If we have chosen a value of p equals to 0.5 for alpha, we look for a value of t that falls into the extreme 5% of the distribution. If we have a hypothesis that states the expected direction of results, for example, that a male graduate assistant salaries are higher than female graduate assistant salaries, then we expect the calculated t-score to fall into only one end of the normal distribution. We expect the calculated t-score to fall into the extreme 5% of the distribution. If we have a hypothesis that states that there is some difference between two groups but does not state which group expected to have higher score, then the calculated t-score can fall into either end of the normal distribution. For example, our hypothesis could be that we expect to find a difference between the average salaries of male and female graduate assistant members, but we do not know which is going to be higher or which is going to be lower. For a hypothesis which states no direction, we need to use a two-tailed t-test. That is, we must look for a value of t that falls into either one of the extreme ends of the distribution. But since t can fall into either tail, if we select p equals to 0.5 for alpha, we must divide the 5% into two parts of 2.5% each. So, a two-tailed test requires t to take on a more extreme value to reach statistical significance than a one-tailed test of t. Calculation of t. A t-score is calculated by comparing the average value on some variable obtained by two groups. The calculation also involves the variance of each group and the number of observations in each group. For example, we have number of observations, mean, standard deviation, and variance of male graduate assistants and female graduate assistants as given. To calculate t, first subtract the mean of the second group from the mean of the first group. Second, calculate for each group the variance divided by the number of observations minus 1. Third, add the results obtained for each group in step 2 together. Fourth, take the square root of the results of step 3. Fifth, divide the results of step 1 by the results of step 4. For example, subtract the mean of the second group from the mean of the first group. We have 17095 minus 14885 equals to 2210. Second, calculate for each group the variance divided by the number of observations minus 1. Third, male graduate assistants is 400,56241 divided by 403 minus 1, which is 400,56241 divided by 402, which comes out to be 99642. And for female graduate assistants, we have 21864976 divided by 132 minus 1, that is 21864976 divided by 131, which comes out to be 166908. Fifth, add the results obtained for each group in step 2 together, that is 99642 plus 166908, which comes out to be 266550. Now take a square root of the results of step 3, that is under root 266550, which is 516.28. And last step is to divide the results of step 1 by the results of step 4, that is 2210 divided by 516.28, which comes out to be 4.28. To interpret the results, calculate the degrees of freedom, look up the value in the table, and interpret the value of t. Degrees of freedom. The degrees of freedom for the t-test is calculated by adding up the number of observations for each group and then subtracting the number 2, because there are two groups only. For example, we have 403 plus 132 minus 2, which comes out to be 533. Distribution of t. The values of t are printed in tables in most statistics texts. The values of the degrees of freedom are listed in a column down the side, and the value of alpha, that is the p-value, are listed in a row across the top. There are different tables for one-tailed and two-tailed tests of t. Find the correct table for the number of tails, then find the intersection of the degrees of freedom and the value of alpha in the table. That value is the value that the calculated t-score must equal or exceed to indicate statistical significance. For a one-tailed test of t with degrees of freedom equals to 533 and p equals to 0.5, t must be equal or exceed 1.645. for a two-tailed test of t with degrees of freedom equals to 533 and p equals to 0.5, t must be equal or exceed 1.960. Interpretation of the value of t. If the computed t-score equals or exceeds the value of t indicated in the table, then the researcher can conclude that there is statistical significant probability that the relation between the two variables exists and is not due to chance, and reject the null hypothesis. This lends support to research hypothesis. In this example, the computed t-score of 4.28 exceeds the table value of t, so we can reject the null hypothesis of no relationship between graduate assistant gender and graduate assistant pay, and instead accept the research hypothesis and conclude that there is a relationship between graduate assistant gender and graduate assistant pay. Remember, however, that this is only one statistic based on just one sample at one point in time from one research project. It is not absolute, conclusive proof that the relationship exists, but rather support for the research hypothesis. It is only one piece of evidence that must be considered along with many other pieces of evidence on the same subject. Now we move on to F-test. A large number of surveys are conducted to draw conclusions about the effect of certain factors or treatments. In testing the significance of the difference of two means of two samples, we assumed that the two samples came from the sample population or population with equal variance. F-test is used for testing the hypothesis about the equality of two population variances or the equality of two or more population means. The object of F-test is to discover whether two independent estimates of population variance differ significantly or whether the two samples may be regarded as drawn from the normal population having the same variance. Hence, before applying the t-test for the significance of the difference of two means, we have to test for the equality of population variance by using F-test. For example, variance in product quality resulting from two different production processes, variance in temperatures for two heating devices, variance in the rate of return of two types of stocks, and so on, are few areas where comparison of variance is needed. Since F-test is based on the ratio of two variances, it is also known as variance ratio test. Some of the properties of F distribution is that, first, all F values are non-negative. Second, it is non-symmetric distribution. Third, its mean is approximately 1. Fourth, two independent degrees of freedom are present, one for the denominator and one for the numerator. Fifth, each pair of degrees of freedom has different F distribution. This test is made to test whether two population variances are equal or not. Comparison of the ratios of two variances is done in F-test. The ratio will be equal to 1 if the variances are equal. All hypothesis testing is done under the assumption that null hypothesis is true. Let xi, where I equals to 1, 2 up till n1, and yj, where j equals to 1, 2 up till n2, be two independent random samples with means x bar and y bar respectively, drawn from normal populations with the same variance. Now let S1 square equals to 1 divided by n1 minus 1 multiplied by sigma I equals to 1 till n1 xi minus x mean whole square. S2 square equals to 1 divided by n2 minus 1 multiplied by sigma I equals to 1 till n2 yi minus y mean whole square. The F statistic is defined by the relation F equals to S1 square divided by S2 square, where S1 square is greater than S2 square. The numerator shall always be greater than the denominator. If s1 square is less than s2 square, then f equals to s2 square divided by s1 square. In the first case, f has n1 minus 1, n2 minus 1 degrees of freedom, and in the second case, f has n2 minus 1, n1 minus 1 degrees of freedom. It can be concluded that the greater of the two values s1 square and s2 square is taken in the numerator while calculating f. If the null hypothesis is true, then the f-test statistic given above can be shortened. This ratio of sample variances will be test statistic used. If the null hypothesis is false, then we will reject the null hypothesis that the ratio was equal to 1 and our assumption that they were equal. There are numerous different F tables. Each one has a different level of significance. So find the correct level of significance first and then look up the numerator degrees of freedom and the denominator degrees of freedom to find the critical value. You will notice that all of the tables only give level of significance for right tail test because the F distribution is not symmetric and there are no negative values. You may not simply take the opposite of the right critical value to find the left critical value. The way to find a left critical value is to reverse the degrees of freedom, look up the right critical value, and then take the reciprocal of this value. For example, the critical value with 0.05 on the left with numerator 12 and denominator 15 degrees of freedom is found of taking the reciprocal of the critical value of 0.05 on the right with 15 numerator and 12 denominator degrees of freedom. For example, two researchers are interested in whether or not there is any variation in the way the results of lie detection are obtained at two different laboratories. They each consider the same set of 30 results. The first researcher's result have a variance of 52.3. The second researcher's result have a variance of 89.9. Problem is, test the claim that the first researcher's variance is smaller. It is desirable for the variances of results of lie detection to be nearly the same among researchers. The level of significance here is 10%. Solution. Let 1 and 2 be the subscript that indicate the first and the second researchers respectively. So, n1 equals to n2, which is equal to 30. Null hypothesis is sigma 1 square equals to sigma 2 square. An alternate hypothesis is sigma 1 square is less than sigma 2 squares. Calculate the test statistic by the null hypothesis, that is sigma 1 square equals to sigma 2 square. The F statistic is F equals to S1 square divided by S2 square, which is 52.3 divided by 89.9, which comes out to be 0.6. The distribution for the test F29, 29, where n1 minus 1 equals to 29 and n2 minus 1 equals to 29. The probability statement is p-value, which is p of f less than 0.582 equals to 0.0755. Now compare alpha and the p-value. We have alpha equals to 0.10 and we can see that alpha is greater than p-value. So make a decision. Since alpha is greater than p-value, so reject null hypothesis. Conclusion. With a 10% level of significance from the data, there is sufficient evidence to conclude that the variance in results for the first researcher is smaller. Applications in forensic science. It is used to test null hypothesis in order to reach some conclusion about an unknown population. These tests are used in forensic science, for example, to estimate whether the distribution methods of suicide are independent of gender. It can be tested using Chisquare with type 1 error. Testing of an hypothesis useful in forensic science can be done using these tests.
To test the null hypothesis, we need to first draw a random sample from the population and then apply a decision rule that uses the sample observation. The first is called a type 1 error. This occurs when the researcher assumes that a relationship exists when in fact the evidence is that it does not. The second is called a type 2 error. This occurs when the researcher assumes that a relationship does not exist when in fact the evidence is that it does. For nominal and ordinal data, chi-square is used as a test for statistical significance. The term degrees of freedom are used to refer to the size of contingency table on which the value of chi-square statistic has been computed. T-tests are tests for statistical significance that are used with interval and ratio level data. The degrees of freedom for the t-test are calculated by adding up the number of observations for each group and then subtracting the number 2. Two independent chi-square variables are divided by their degrees of freedom and then its ratio is calculated. The ratio leads to the formation of F distribution.